I just want to go through a couple of questions that might trick you up if you don't realise one thing. So if you remember from your work on the idea of real roots and how many real roots there may be for a quadratic, you'll remember that if you draw a graph, you can have three scenarios. You can have two intersections with the x-axis, i.e. two real roots. You could have one sort of repeated real root, it just sort of touches the x-axis and then bounds back up again, or it might be also negative, in which case you'd have that scenario. Or you could have no real roots because the quadratic curve does not intersect the x-axis. So, and you remember the discriminant, so for any quadratic of the form of ax squared plus bx plus c being equal to naught, you have the discriminant, which is b squared minus 4ac. If it is greater than 0, then you have two real roots. If b squared minus 4ac is equal to 0, you have one real root. And if the b squared minus 4ac is negative, then you have a situation where you have no real roots. So if we use that idea with question 6 onwards, you can apply that. I'm going to do an example here. So we're asked for which values of k will give a quadratic that has real roots. Now that's an equation, okay, but you're getting a range of values. There's an inequality going on here. So what I need to do is I need to pick out the b. So b is k minus 4, okay, a is 1, and c is k minus 1. So if I'm going to do the discriminant, anytime basically you see a question asking you about are there any real roots, okay, it's a red flag to doing b squared minus 4ac and see what happens. So b is k minus 4, so you square that. Take away 4 multiplied by a, which is 1 in this instance, and c, which is k minus 1. So we just tie that up. So we've got k squared minus 8k plus 16. That's the expansion of the k minus 4 all squared. And then if we expand this part, we end up with minus 4k plus 4, which ties up all told to be k squared minus 12k and plus 20. So if there are to be real roots, okay, real roots is plural, okay. If it was a real root, you'd have to make sure on singular, okay, repeated, then this would have to be equal to 0. Now, if you want more than one distinct real root, then it has to this discriminant has to be greater than 0. Now, just very quickly, you could argue that it hasn't been particularly clear. If it said, real roots as in one separate roots, or if you're willing to accept that a repeated root is still two roots, but they're just the same number, you could arguably put in the equals there. Anyway, let's solve this. Okay, so quadratic greater than or equal to naught. So we're going to firstly factorize it to find the roots of this quadratic. And so two numbers multiply together to make 20 and add together to make minus 12, which is minus 2 and minus 10. And it factorizes to k minus 10, k minus 2. So we have a situation where the critical values are 10 and 2. And we want the values that will give us something greater than 0. Well, again, my natural reaction would be to imagine this graph. Okay, basically what we're saying here is it's crossing at 2 and 10. It's a positive quadratic, so it's a U shape, and we want it to be greater than or equal to 0. So greater than or equal to would be in this region here and here. So your x values are going to be numbers less than 2 or greater than 10. So we can say that k can be less than or equal to 2, and along with that you can union the scenario where k is greater than or equal to 10. So using the same process, you should be able to do questions 6 and 7. And I'm just going to quickly go through question 8 here now. So again, not dissimilar to the other ones. Find the range of values of p. Okay, it's a different letter, but still the same idea. It has real roots. So real roots, again, what we're wanting is discriminants being greater than or equal to 0. We want to take my values of a, b, and c and use those in that discriminant. So b squared is p plus 3 all squared minus 4 lots of a lots of c. So that's my discriminant. That ties up to become p squared plus 6p plus 9 minus 4p squared, which ties up further to being minus 3p squared plus 6p plus 9. Okay, and what I would say to you here is I could appreciate the fact that 3 is a common factor. So when I'm dealing with factorizing this, I could choose to potentially divide by 3. If I divide by minus 3, okay, then I'd need to deal with the fact that I need to turn the inequality direction in the other direction. So for example there, I've just factorized it. I had minus 3 as a common factor. I brought that out, and eventually I can look at, now you can see in the very last line that I've changed direction inequality because I effectively divided by minus 3 both sides. So here we have a quadratic which is it's a positive quadratic. It crosses at -1 and 3. They're the solutions of the critical values that are produced from that inequality. And we want it to be less than 0. So what we're talking about is this bit below the x-axis. So the values that fit the criteria are the values between -1 and 3. So we have a solution of p must be greater than or equal to -1 and less than or equal to 3. So that's the range of values that fits that criteria. And lastly, and by the way, just very quick, again, don't forget to potentially always check to see that your answer seems correct. So if let's take, for the sake of argument, 0 is a really nice, easy number between those two, or I could take 1 as an alternative. So the key idea is if I were to put either 0 or 1 into this expression here, okay, what would I get? Okay, so if I put 0 into that, okay, minus 3 lots of 0 squared plus 6 lots of 0 plus 9, does that, or is that greater than or equal to 0? Yes, it is. So I definitely picked the right range. It's not outside of -1 and 3, i.e. below -1 and greater than 3. It's between, okay, a value of between -1 and 3. Assuming I've picked the correct critical values, they give me the right answer. So I'm happy with that. Now, specifically it says x is -2 is a root of the original equation given. Okay, find the value of p. So putting this value of -2 into the original equation, okay, we're going to get p lots of -2 squared plus p minus 3 lots of -2 plus p. And for -2 to be a root of this equation, then this equation should hold, i.e. indeed, as it's stated, it should equal to 0. So if I tidy that up and solve it, I get the answer of p is equal to 2. So that is the value of p, so singular, that would work if -2 was indeed a root of that quadratic.